Welcome back. In the last session, we were discussing this. We have just started the topic that how the bacteria acquire resistance against the beta-lactam antibiotics, and one of the major cause of that is that it produces enzymes which are classified as beta-lactamases, and these beta-lactamases are named because it hydrolyzes the beta-lactam ring, and if you can break the beta-lactam ring, then all the beta-lactam antibiotics are going to lose their activity. Okay. So, now the question is, what is the difference between transpeptidase and beta-lactamase? That should be made very clear. Transpeptidase is a serine based enzyme, and then the serine attacks the beta-lactam ring, breaks the beta-lactam ring, makes an acyl enzyme complex, and that stays there for a long time. On the other hand, the beta-lactamases, there are different classes of beta-lactamases. One of them utilizes serine. So, if it utilizes serine, again the mechanism is virtually same. The serine attacks the beta-lactam ring, form the acyl enzyme complex. However, now the attack by water is very fast. So, this is the penicillin, and then you have, if it is beta-lactamase is a serine protease. Okay, serine, not protease, it hydrolyzes this beta-lactam bond. Okay. So, the which attacks the carbonyl, this breaks, there is substituent here. So, O, then the enzyme, and then you have NH, S and this. Okay. In case of beta-lactamase, now water immediately comes very fast and frees the beta-lactam enzyme, the beta-lactamase enzyme, and leave the hydrolyzed penicillin, which is ineffective. Okay. So, plus the enzyme, this enzyme is beta-lactamase. For transpeptidase, this next reaction, that means attack by water, is very slow. So, this is the difference, and this difference is causing havoc, that a beta-lactamase enzyme has a very high turnover number. So, basically high turnover number means one molecule of beta-lactamase can hydrolyze several molecules of penicillin. So, makes it ineffective. Okay. And this is the major cause of concern in today's and is bacterial and infection scenario. Okay. Because the beta-lactamase enzymes are grouped into 4 classes. Okay. Class A, class B, class C and class D. At least for today, at this point of time, these are the 4 different beta-lactamases. What is class A? Class A is basically the gram negative, say, organisms which were earlier treatable with ampicillin or amoxicillin, organism which were earlier treatable with amoxicillin or ampicillin, those type of drugs. Okay. That means, this class A beta-lactamase hydrolyzes ampicillin or amoxicillin. Okay. By a serine, the active site is a serine. Okay. Class B is, it hydrolyzes penicillins, it hydrolyzes cephalosporins, but the most important is that it hydrolyzes the carbapenems. We have not talked about carbapenems, I have showed you only the structure, the skeleton, but carbapenems are powerful enzymes which are in the market now. It is one of the last defense that we have, that if the infection is very resistant, then people start giving the carbapenems. Okay. But there are now enzymes which are called class B enzymes, which utilizes a metal ion to hydrolyze the beta lactam ring. So, it is not the serine OH, it is now metallo. So, this is a metallo beta lactamase. Then class C is basically the it hydrolyzes the cephalosporin molecules, and class D it hydrolyzes the oxacillin, that is another type of penicillin which was in the market, which has got very good resistance earlier against this beta lactamases, but now there are enzymes which are called class D beta lactamases that hydrolyzes very good effective antibiotics like oxacillin, which is a penicillin by the way, but it has got a different side chain oxacillin. So, these are the 4 classes. Out of these, most difficult one is this class B, because it is a metallo beta lactamase. So, its mechanism is different from the earlier the other 3, and it extremely difficult to treat this type of the type of infections which are caused by microorganisms producing class B. And you will be surprised, or you will be, I think you should know this, that one bacterial strain which produces the class B metallo beta lactamase enzyme is what is called the NDM bacteria, NDM harboring bacteria. What is NDM? New Delhi beta lactamase. So, this strain was originated not very maybe 10 years back, New Delhi metallo beta lactamase. So, NDM strain, any NDM strain, it could be Klebsiella pneumonia, or Klebsiella is the one which is very dangerous, it causes pneumonia, and they are now becoming very difficult to treat because of this NDM producing or NDM harboring bacteria. What is NDM? New Delhi metallo beta lactamase. Okay. So, you see that gone are those era that when we are really safe, because we had many antibiotics in our hand, like erythromycin is one group of macrolide antibiotics, ciprofloxacin, that is another group. I showed you one slide where the different targets have been shown, that some targets the nucleic acid, some targets the transcription, some targets the translation protein synthesis, some targets this synthesis of the cell wall. Okay. So, different targets, different antibiotics are there, ciprofloxacin, then you have the erythromycin, that is macrolide antibiotics, you have cyclic peptide antibiotics, you have carbohydrates based antibiotics, amikacin, those type of molecules. Then you have this beta lactamase, this beta lactam class of antibiotics, and you have vancomycin, polymyxin. So, lot of antibiotics are there, but the problem is many of these antibiotics have serious side effect, because they are targeting certain things, they are targeting something which is also there in the host. So, that is where the problem lies, except for penicillin and possibly vancomycin, because vancomycin also targets the cell wall biosynthesis. Okay. Now, let us see the major problem of this beta lactamase producing microorganisms. They are mainly with the gram negative bacteria. Gram positive bacteria are easier to treat, because the cell wall is outside, cell wall is exposed to the outside world. But in case of the gram negative, first you have this outer membrane which is hydrophobic, then you have a space which is where this bacteria produces the beta lactamase enzyme. So, they are basically harboring, they are traversing here, they are looking for molecules which come here, and then if it is penicillin, they are going to destroy it. Then the cell wall, which is much thinner, and actually here your your cell wall, that means your transpeptidase is here. So, the problem is that if a molecule, penicillin molecule enters, it cannot go to the transpeptidase, because it has to cross the layer, a periplasmic space where the beta lactamase is present, okay, where the beta lactamase is present. So, it is a very difficult or challenging task to treat the gram negative bacteria. So, if somebody says why gram negative bacteria are difficult to treat, this is because first of all the molecule has to cross this hydrophobic barrier, and that is difficult, because you need carrier molecules to take it through the hydrophobic barrier. However, there are some certain channels, because bacteria also need some molecules, some nutrients which has to be given from outside. So, that goes through pores which are called porins, or these are the channels through which small molecules enter and go there. So, if penicillin by chance enters here, now the beta lactamase is here, that is going to destroy the penicillin. So, that was the major problem. So, 70s, late 70s, when this then cephalosporins came into the market, and lot of new cephalosporins were having resistance to this to the beta lactamase producing microorganisms. So, cephalosporins became the savior. Then first generation cephalosporin, second generation cephalosporin, but people were running out of option, because the bacteria is also changing its character, okay, changing its character. So, new antibiotics were required, because felt that yes, it is time that we should discover new antibiotics, or at least we should discover molecules which takes care of this beta lactamase. Okay. That actually search gave the, so this is what is the reaction, beta lactamase hydrolyzes the penicillin. I already told you that there are various mechanisms. It can do it by serine, or it can do it by a metal ion, metal ion. Like if it is M plus, so obviously the metal ion chelates to here, like metalloprotease, you know. So, very similar mechanism, it activates the carbonyl, and then this is broken very easily only by water. So, the enzyme does not have to participate directly, and usually these metallo-beta lactamase have two metal ions, one for the coordination to the carbonyl and another for this negative charge to be stabilized by the second metal ion. Okay. So, what I was telling, that the 70s, late 70s, people, this various pharmaceutical companies frantically search for molecules which have stability towards beta lactamase, and what they found, that a molecule which is known as clavulanic acid. Clavulanic acid, the structure is again a beta lactam compound with the oxygen and then an exocyclic double bond, and this is what is clavulanic acid. So, what is the difference with penicillin? First of all, it is a oxapenem, and then it does not have the side chain here, and it has oxygen, and this oxygen is very funny or very interesting in the sense that there is a double bond here. So, this has got a very good leaving group character, because if it is O minus, then it can resonate with the double bond. So, this oxygen, unlike in case of penicillin where you have sulfur, there is not much stability of the sulfur, because it is not a, although sulfur is quite a good leaving group, but it is not assisted by any double bond like this. So, clavulanic acid is a molecule which was discovered again by Beecham Pharmaceuticals, and what they found, that this molecule is a very potent inhibitor of beta lactamase. But at that time metallo-beta lactamase was not there. Okay. Protein inhibitor of beta lactamase means that serine class of beta lactamase, and that was prevalent at that time, inhibitor of beta lactamase. However, this itself has very weak antibacterial activity. antibacterial activity. So, it is an inhibitor of beta lactamase, but it is not a good antibiotic. So, if you take clavulanic acid, it will not treat you, because it will just inhibit the beta lactamase, that is all. But the cell wall biosynthesis will take place, because it is not a good antibiotic. If it is not a good antibiotic, that means it targets the beta lactamase enzyme, but it does not target the transpeptidase. Okay. So, quite interesting molecule, but then people are very clever at Beecham. So, what they thought, that better do this, that take a penicillin which is hydrolyzed by beta lactamase and mix it with clavulanic acid. Okay. If you do that, take this combination, then what will happen? Clavulanic acid, because it has got very high affinity for beta lactamase, so it is going to stop the beta lactamase from attacking the penicillin, and so the beta lactamase is busy with the clavulanic acid, and by that way penicillin sneaks through and then attacks the transpeptidase and stops the transpeptidase enzyme. In fact, this combination is one of the life saving drug today. It is called, there is a compound called augmentin, which is a mixture of amoxicillin and clavulanic acid. Clavulanic acid. So, it is a combination drugs. Clavulanic acid targets beta lactamase, takes care of the beta lactamase, and amoxicillin now attacks the transpeptidase. More interesting is that in presence of clavulanic acid, amoxicillin becomes very powerful antibiotic. Means earlier whatever the antibacterial activity amoxicillin had alone, when there was no beta lactamase, if you had to take 500 milligram to have the same effect now in presence of clavulanic acid, you need much less amount. Okay. So, that means amoxicillin not only now targets the transpeptidase in presence of clavulanic acid, its power also is increased in presence of clavulanic acid. This is what is called synergistic effect. Synergistic effect. Synergistic effect is that suppose you have a drug A and that has got a potency say P1, and now you mix that with B, now the potency is say 10 P1, that means 10 times more potent in presence of B. How that does happen? In this synergism can be very easily described by comparing with a real life scenario. You all this is not chemistry, but it can explain this very well, this synergism. You know Lionel Messi, everybody knows, he is a very good footballer. He plays for Barcelona and scores many goals, but when he plays for Argentina, he has not produced that form which he showed in Barcelona. Why is that? That means in Barcelona it is the same. Now, instead of the molecule, you have the same man, Messi. He plays so well in Barcelona, but not that well for Argentina. So, there must be some synergistic effect going on in when he plays Barcelona, and that synergistic effect, if you are a football fan, you know that there are players called Iniesta, whose name is Iniesta, and Xavi. They are the clavulanic acid of Barcelona. So, they supply balls and which Messi can convert and feel also very strong. So, that is the synergistic effect, that in presence of good footballers, the other player shows much better efficiency than when those players are not there. Okay. So, clavulanic acid and penicillin combination is basically a miracle, but that always remember, bacteria is also very clever. Clavulanic acid was there, so everybody thought that now the answer is there, but actually this battle between bacteria and human being will continue forever, because bacteria wants to survive, we also want to have a healthy life. So, bacteria wants to mutate, have different strategy, and then like this advent of the metallo-beta-lactamase where clavulanic acid does not work. Okay. So, for treating the infection by metallo-beta-lactamase, carbapenem, I think I have the structure of carbapenem possibly, let us see. So, this was this I told you about the about cephalosporin, how it works, and then yes, this is the carbapenem that is in the market today. See, it is a carbapenem, this is carbapenem, sorry, I am sorry, carbapenem, because it is a, it has got a double bond. Okay. So, carbapenem antibiotics has different heterocyclic ring here, and in the side chain it is always hydroxy methyl group. So, there is drugs which are called meropenem, ertapenem. Ertapenem is all depending on this R2, R1. So, lot of research is being spent on developing new types of carbapenem, but these are the ones which are in the market today. Remember, this alone can withstand the beta-lactamase, this alone can target the transpeptidase, the same molecule takes care of the, so beta-lactamase does not hydrolyze, and then the same molecule the transpeptidase is inhibited. Okay. But today at 2019 the scenario is that because of this advent of NDM strains, carbapenems are also not effective against this. Carbapenems also failed, it does not work. So, then what is the answer? This situation is very bleak. If people have this NDM infection, then unless we get new antibiotics, I think the last answer is polymyxin, but polymyxin is very toxic also. So, the patient may not survive, that is the problem, but polymyxin can kill the NDM strain, but the problem is it may not, because of the toxic side effect, the patient may not survive. So, things are very grim unless we have some mechanism to take care of this NDM problems. Okay. So, that is carbapenem. Again, now the I told you that there are some drugs like aztreonam. This is also the one which is prescribed in case of NDM based metallo-beta-lactamase MBL infections. Aztreonam is one. Now, you can actually ask that why, because earlier you have been told that it has to be a bicyclic network to increase the electrophilicity of this carbon. Okay. But if you do not have bicyclic framework, how come that this is also opening very rapidly? You see the group here, you can see you can bypass the bicyclic framework by putting an electron withdrawing group here. If you put an electron withdrawing group, then also that is going to activate, that also can activate the opening of the beta-lactam ring, and exactly nature has done that, put the sulfonic acid group here. So, that is an electron withdrawing group, and that helps the carbonyl to be attacked by the enzyme, that serine in the transpeptidase. So, this is one, and there is another group of antibiotics which are called nocardicins. This is also a monocyclic compound. This is also a monocyclic compound, and they are also having antibacterial activity. So, that means the myth that it has to be bicyclic, that is not true. These two classes of compounds have shown that monobactams, they are called monobactams because they have only the beta-lactam group. So, the monobactams are there which can show activity, but in order to do that, it is better that you have a electron pull from the nitrogen. Okay. Now, the question is why there are, apart from clavulanic acid, because every time you cannot use clavulanic acid, There you have to always have different varieties of inhibitors of beta lactamase. Okay. Clavulanic acid is very good, that is true. It is again it is a microorganism made compound. Okay. Now, there are synthetic compounds, sulbactam. What they did? See, it is basically a penicillin without any side chain. I think the numbering is again 1, 2, 3, 4, 5, 6, 7. It could be that the numbering goes like this, but we will have to check that whether different text follows different numbering. But whatever you follow, this becomes 6 in penicillin and this becomes 7 in cephalosporin. Okay. Now, this is now oxidized to a sulfone. Sulbactam is a penicillin sulfone. So, what happens if you make a sulfone, that means you are making this a good leaving group, much better than your only sulfur, okay, because that is an electron withdrawing group, it is now pushing. So, if the nucleophile attacks here, that goes there, that opens up. Now, question is, after opening up, what happens? I will go to tell you next. In clavulanic acid, the same thing happens. This is a very good leaving group, so that leaves. But what happens after that? Why the enzyme is inhibited? That is the $1,000,000 question. You have another compound avibactam, which is entirely different, but again it is a bicyclic compound and again the nitrogen is attached to a sulfonate. So, this opens up by the your nucleophilic serine in transpeptidase or in beta lactamase. So, they are actually beta lactamase, they are good beta lactamase inhibitors, they do not have, they are good beta lactamase inhibitors. Do not get confused, some molecules which are beta lactamase inhibitors, they are very weak antibiotics like clavulanic acid, like sulbactam, like avibactam, like tazobactam. These are only beta lactamase inhibitors, except the carbapenems. The carbapenems are the ones which are beta lactamase, they are not attacked by beta lactamase, or even if they are attacked by beta lactamase, the beta lactam enzyme is inhibited. Okay. At the same time, they are very good antibiotics. Okay. So, that has to be very clear. So, now the question is, what is the mechanism of this inhibition of beta lactamase by clavulanic acid? We take the clavulanic acid as the example. So, our clavulanic acid molecule is where? I think here that is not written. So, clavulanic acid molecule I write here NO, forget about the stereochemistry for the time being, double bond CH2OH. This is clavulanic acid. So, the first step in beta lactamase is that it attacks the carbonyl, this goes here, comes back and that opens up. Okay. So, from here we can start. So, the serine has attacked and opened the clavulanic acid beta lactam ring. Then what happens? Then, as I told you that this is a very good leaving group, that oxygen. So, the lone pair goes here, that comes here and this takes up a proton. Okay. This takes up the proton. So, that means you get this iminium, this imine complex as the iminium ion. Okay. Now, there are several mechanisms, because it is all done by mass spec and some IR spectroscopy, several mechanisms. So, what they did, add the beta lactamase and try to identify different metabolites which are obtained from clavulanic acid by mass spec. And one of the mechanisms says that you get, once this happens, so you get O enzyme, okay, and then you have this iminium ion NH plus, then you have CO2H here, you have a carbonyl here and you have this OH, that is the same compound which is written here. Now, there are many things can happen. This is a beta keto acid. So, decarboxylation can take place, and if you look at this slide, decarboxylation has taken place here, it can decarboxylate. Okay. So, what they got this type of species, that means it is just only 3 carbon, but without going into such details, what is generally believed is that this iminium ion now tautomerize into the enamine. You know the enamine imine tautomerism, that means double bond is here now, and this becomes NH and CO2H, and then the rest carbonyl and this OH. Okay. Now, this has become a good Michael acceptor. This has become a good Michael acceptor. So, what will happen? The enzyme which is acyl enzyme, there are many things that can happen. First of all, if I ask you which ester is hydrolyzed faster, a propionyl ester or an acrylic ester? The answer is that the acrylic ester will be slower because of this conjugation. So, that reduces the electrophilicity of this carbon. Okay. So, now when the double bond is here, the enzyme cannot free it because the hydrolysis will be slow. That is number one. Number two is the enzyme is actually a very big molecule. See what happens here, we are looking only written as E and Z, but actually the enzyme is like this. Na? All the whatever is happening is inside the cavity of the enzyme. So, this then the double bond, then you have this NH and the other part of the clavulanic acid. So, what can happen? This is a very good Michael acceptor. So, if there is a nucleophilic amino acid in the enzyme, that can come and attack this carbonyl and undergoes a 1,4 addition. And finally, what you get is an attachment with the a covalent attachment with the enzyme. So, even if the enzyme now freeze here, means water comes and hydrolyzes this, this is already attached, the other portion of the enzyme is attached to the clavulanic acid, the hydrolyzed clavulanic acid. So, that can now, so that means it is covalently linked to the that modified clavulanic acid. So, that means it is irreversibly inhibited. I can again write it in a better way. I think the way I did, I was not, let me see whether there is any blend. Yes. So, what again I write, this is your clavulanic acid. By the way, this is one of the mechanism, because the mass spec has given many peaks. Okay. Of course, that does not tell you, because in mass spec there may be fragmentation also, that is not a that is not the sacrosanct that has to happen. So, now you have a beta lactamase like this. Okay. I write the big enzyme now and an XH here. So, this is going to hydrolyze this, that goes here, in one step you can show it, and that comes here. So, if that be the case, so that means now XH and you have O, then the CO, then you have double bond N, what you have is a double bond here and then a carbonyl here, CO2H here, and then this CH2, CH2H. Now, this tautomerizes into O, CO, double bond here, then actually you should not write any stereochemistry here, it could be cis or trans NH, and then you have this CO2H, CO and CH2, CH2H. So, what I am saying now XH is present. So, X now attacks here and forms the covalent connection. So, even if it is hydrolyzed, the enzyme stays with the this modified, that hydrolyzed clavulanic acid, transformed clavulanic acid. So, this is an irreversible inhibition, because covalent bond formed. Now, the question is it a suicide inhibitor or is it an active site directed irreversible inhibition? This is a suicide inhibition, because the molecule has been accepted first as the normal substrate, what the beta lactamase does. Then it is transformed into a reactive species, and that reacts with the active site amino acid residue. Okay. So, that is the best example of a suicide inhibition. So, this is the mechanism, and all penicillin, that sulfone whatever I said, tazobactam or your sulbactam, they all work on this principle, that the beta-lactamase comes, attacks this opens up and that goes out. As soon as this forms imine, that tautomerize to the enamine and then the enzyme active site adds on to the double bond. Okay. So, the trick is to, if you want to develop a new beta-lactamase inhibitor, you have to have a good leaving group at this site. Okay. That is the trick to make the molecule. However, the molecule has to be accepted by the enzyme. Clavulanic is such a molecule, penicillin derivative is such a molecule. Okay. So, that is the we have now done the penicillin chemistry in quite detail, that how penicillin works and what are the different modifications, what are the different natural products which contain beta-lactam, where you can use them, then what is the genesis of resistance in against the beta-lactam antibiotics, and then how to overcome them and how to utilize beta-lactamase inhibitor. Okay. So, next we will go to other topics in the next session. So, this session ends here. Okay. Thank you.